Hi, I'm Dustin Carlino, and this is a pre-recording of a talk that I'm going to give tomorrow to the online Seattle Rust meetup. And the talk is about building a traffic simulator in Rust. So let's get started. Um, so about 2 years ago, I quit my job to start this project called AB Street. And AB Street is a little bit of an identity crisis between a game and an urban planning tool. But the idea is it's a realistic model of traffic in Seattle, traffic of all sorts. And the player of the game or the user of this tool can decide to reallocate road space to prefer different modes of transit or of transportation. So, for example, you can take space that's usually dedicated to parking cars or just giving cars room to move and say, what happens if this becomes a bike lane or a bus lane, and measure the impact on all groups. And so it's a little bit of a involved story why I started this project, but at least part of it is that I saw a lot of people around me in Seattle that had ideas for changes. I had seen proposals for pedestrian all-walk cycles downtown instead of having vehicles conflict with, or vehicles turning right conflict with people walking. Seen a lot of plan changes when new rapid ride lines go in to build bike lanes. I've also seen awesome plans for bike lanes that wind up getting canceled because different people are concerned about the impact on parking. So for a bunch of reasons, I decided I wanted to study this sort of thing and make it really easy to do so. And so let's say you had an idea to improve a city today. What could you do? Sort of the industry standard is this software called Vicim. The problem here is that you have to buy a pretty expensive license to use it unless you work in the government or part of a university that has a license. It's also a little bit hard to use, and as far as I can tell, you have to manually draw the map that you want, and there's not really a way to import existing data, like say from OpenStreetMap. Then there's also some open source traffic simulators out there. The big ones that I know of are Sumo and MatSim. But these are a little bit hard to set up, and the user interface is also not quite easy to understand, and so it'd be not the easiest way to study the kind of changes that I was interested in. Then on the other end of the spectrum, you have computer games like City Skylines, and particularly a mod called Traffic Manager President's Edition that are extremely easy to use, but they're not exactly designed to measure real cities. And one kind of modeling gap that I'll point out is that when a driving trip is happening, somebody will walk outside of a building and take a car out of their pocket and just start driving. There's no notion of contention for parking spaces. So for this reason and a bunch of others, I decided to start AB Street. And before I continue, it's been a very long, lonely journey for a good chunk of these 2 years. But recently, the team has grown, and I want to acknowledge the people that have joined the team and put in hard work. Particularly, Ewan is a student at UW who joined the project in November, and she helps with, she's defined the sort of user experience and user interface design. I've also gotten help from some different people on the art direction of the project. And then recently, Christopher Klein joined and has been giving some game design advice. And then just 2 or 3 weeks ago, Orestes Malaspinas is a researcher at the University of Geneva, and he got in touch because he's interested in modeling some of the stuff that's happening right now in kind of an agent-based simulation. But I'll get to that in a bit. So this talk is going to go all over the place. I'm going to talk about a bunch of implementation details, stuff that's like particular to Rust. But you don't really need a background in Rust necessarily to understand anything. And I'm also, the talk is just going to kind of go everywhere. So in the real version of this talk, this is where I would tell you to interrupt me with questions at different points. Let's get started, as I always do, with a demo, just to like have an idea of what we're looking at. And there's quite a lot to kind of show here, but I guess let's see what we want to focus on. So this is a map of a very small section of Seattle. And if we kind of zoom in, we can see a lot of detail. So for example, this is a 4-lane road with parking along one side, and looks like right now a number of cars are kind of using these parking spaces. And we've got sidewalks. We have here a traffic signal that kind of changes state over time, allowing different movements. And I'm going to talk in detail about all of this stuff later, but just in short, this data comes from OpenStreetMap and a few other places. Kind of the thing that is built on top of this detailed map of a section of Seattle is a traffic simulation. So let's actually just kind of jump forward to when there's some more traffic, just to have something interesting to look at. That's probably fine. So if we zoom in at an intersection here and probably slow down time, you can see this is like a cyclist. They're biking along this road, and we've got a few cars behind them moving around. So here we have a stop sign. So you can see that car yield at the stop sign. You can see this car is ending their trip. They have been driving somewhere. Now they're parking, and we will see the little person get out and probably walk into some building. It's really hard to click on people when they're moving. Let's do that. Yeah. So this is a trip that someone's just finished. And so there's sort of a whole bunch of stuff in this simulation, but I guess one thing that I want to focus on is the idea of improving a particular commute. So in this little slice of the gameplay, the goal is to optimize the commute of this one particular person. And I've actually already sort of identified the problem and made some edits. And I don't want to spoil the not so secret solution to this first little puzzle, but the hint is bike lanes help. Anyway, so actually, okay, I'm not sure what I'll show tomorrow in the real talk of the demo. So for the sake of this recording, I'm just gonna go back to the slides. That's a little bit easier to talk about. Yeah. Okay. So all right. All right. So let's jump into some of the details here. How is the map and AB Street of Seattle built? So the sort of an entire other talk that would explain all of this, but I'm just going to cover a few details here. In short, some different data sources, most notably OpenStreetMap, which is sort of a Wikipedia plus Google Maps crossover, and some data that's specific to Seattle from King County GIS. These are kind of read in, and they produce this intermediate raw map format. And then there's some problems that have to be kind of manually fixed, and there's this editor to do that. And so the fixes plus the raw map yield the final map. So jumping into some details and some code, the map in AB Street is sort of it's got a bunch of different objects. So and some of them have kind of graph relationships to each other. So for example, you have roads which go between two intersections and consist of a bunch of different lanes. And so there's a parent-child relation between lanes and roads. And at first it was not entirely clear how to model this sort of thing in Rust. So the way that I'm doing it is the final map object just has like a list of all the roads, lanes, intersections, and so on. And these are just indexed with normal usizes. And Rust lets you get this type safe wrapper around the usizes. And so I have like lane ID, road ID, and so on. And then methods on map that kind of let you reach in and grab one of these in particular. But the sort of interesting question is, how do these objects refer to each other? So in essence, I'm using the ID, IDs, which are just the array indices, as pointers. And so like a road object has a list of lane IDs in both directions, and it knows the intersections that the road points between. And so it's a little bit weird to not directly use pointers to represent this, but it would be kind of complicated to do so because of all the circular references and stuff. And sort of the reason this is overall safe is that once built, the maps are pretty much immutable. You don't just delete roads or lanes. And so there aren't any logic bugs with deleting a lane and forgetting to update everything. The exception is that the player can edit the map, and like this is sort of a complex process to go through and fix up everything that references each other, but that's very tightly contained. And so that's kind of the approach there. So getting into a little bit of details about how the map is built. So OpenStreetMap represents roads as something called ways, and the ways go between a bunch of different intersections. Like it'll represent like a long stretch of a road. So for example, this red north-south road crosses two intersections. So one of the first steps is to chop that up into pieces so that roads are just segments in between exactly two intersections, and then to figure out the number of lanes associated with each segment. So OpenStreetMap has some key value pairs associated with the ways. And so, for example, it might say something like there are 4 lanes, presumably 2 in each direction. There's a designated bicycle lane, and on the one direction of the road, it even tells you specifically what turn lanes exist. And then from the King County GIS dataset, there's some information about parking, but that data is a little bit imperfect, but it's a start. So one of the complicated problems is OpenStreetMap just gives you the center line of a road as geometry, and we have to turn that into thick roads. So basically from the number of lanes and from some guessed values for width per lane, you can take the original center line and project out to get lines representing like either side of the road. So for example, here you have like the 2 red lines of this road, 2 green lines here, and 2 blue lines here. So then you want to turn that into the intersection geometry, which is the kind of the polygon that's separated. It's the piece of the road that's distinct from all of the individual roads. And so roughly the way that I do that is to take all of these like edges of the roads, find all of the intersections between them, and then every time you get one of these intersections, project back and find out where along the original center line that intersection point kind of comes from. So and then you trim back the road to that point, and that kind of gives you so all the green sections are the roads that have been trimmed back, and you can kind of take those intersection points, the original intersection points, and these like trimmed back points, and use it to get the orange polygon, which is an approximation of like what the intersection shape looks like. There's definitely a bunch of edge cases here, so sometimes the points you get for the intersection polygon kind of double back, and you have to like find the center of the polygon and like go in clockwise order and to make sure you end up with like a nice convex polygon. And then there are also points that are like effectively equal to each other, or they're just like there's a very small difference, and so you have to kind of choose a threshold and deal with that. And I'd like to say that this process works well, but it turns out it doesn't. So here's an example of something that looks really buggy. You have like 3 intersections kind of smushed on each other, and it's really not clear what's going on here. So if we kind of look at the intermediate form, the problem is that OpenStreetMap represents the section as a bunch of distinct ways connected to each other. So you have this piece of the road, this piece of the road, and this one, which kind of makes sense. But then there's also 2 very small pieces of the road in between here, and then maybe arguably like this little piece. And if you just like take this algorithm and run it on OSM data like this, you wind up with this mess. And it kind of gets worse. So this is a section of Seattle near the Montlake and 520 overchange. And there's a whole lot of stuff going on here that doesn't make any sense. And if you kind of look at the raw OSM data, it's not much easier to understand. There are just a whole bunch of very small nodes next to each other. And kind of the root problem here, this particular area, this road is not actually, it's like in OSM it's modeled as 2 one-ways going opposite directions, but in reality there's not this big median in between. But that's the way it's mapped in OSM at the moment. So in short, this is a hard problem and not solved yet. So what I'd like to get to is knowing kind of the proper geometry of roads so that the map in the game can be a lot easier to understand and a lot more realistic. So this particular map shows you kind of the detailed shape of this weird intersection at 23rd and Madison. You can even kind of see like the width of the sidewalk and kind of infer that like these parcel lines are probably, if not building boundaries, there might be some like stuff in the way there. And here you have this like little triangular pedestrian crossing island, and like it all looks very nice. So this data comes from a Seattle government website called Streets Illustrated, and this data comes from like a vector layer that they have, but apparently they can't release that layer because of data licensing stuff. Like the company who produced it, won't let them make it public data, unfortunately. But I'd like to get to this sort of thing eventually. So moving on with more interesting stuff that happens with maps. I'm sure you noticed earlier that like the different maps that you can load are not all of Seattle, and like obviously you have to pick some boundaries somewhere. And so at the boundary of the map, you have these like border intersections that lead on or off the map. And so one of the interesting things that happens is that at some point in time, I was simulating a car, and the car sort of reached its destination and then was looking around for parking. And at this point, I think the cars were like kind of randomly picking turns to take in order to find parking. And this particular one like wound up getting on 520 and just like driving off the map and crashing because some code didn't expect that to happen. So in fixing this problem, I realized that before cars need to like stop and look for parking, you actually have to consider kind of the strongly connected component of roads that you can reach when driving. So like all the green roads here, if you start on any one of these roads, you can get to any other green road by driving, and like just stay within this graph and like it's fine. But if you want to start or end in any of the red sections, then you might not be able to reach everything else. And that kind of intuitively makes sense. All the stuff on the border, like if you start going on like north across the Mountain Lake Bridge, like at the edge of this boundary is a border intersection. You can't just like do a U-turn. And so if you start here, of course you can't reach the rest. Like mostly this makes sense, but you might notice this one little road here, which is like by Roanoke Park. And so zooming in, this is actually true to reality. Like I know this area well. You have technically a two-way residential road just on the east side of Roanoke Park. And then for a very small section, it's technically a one-way. And then it like comes out to, what is this, like Roanoke or Del Mar. And so technically, I'm not sure, like cars, if to go like north on this direction of the road, cars would have to like do some, three-point turns in driveways and stuff. But in AB Street, we're not modeling that. So like this section of road is just completely unreachable by all cars, which it's just a funny sort of bug. Okay, so this is kind of the end of the section of the talk about the map model. Next, we're going to talk about the traffic simulation, and I'm going to drink some water really quick. Okay, so we have this hyper-realistic map of Seattle, and now we want to simulate a bunch of different agents on it. Traffic simulation is usually done, or is sort of a field that's existed for a long time, and there's a whole bunch of different ways of doing it. A bunch of them kind of use sort of fluid dynamic models inspired from physics, or cellular automata, or other stuff like that. But kind of the sort of traffic simulation that I'm interested in is agent-based, and so individual drivers, pedestrians, bikes, buses, these are kind of the lowest level of detail in the traffic simulation, and they're kind of like independently making choices over time and moving around. And the basic movement model is pretty simple. Cars, bikes, and buses are in the road. They're kind of in one lane at a time, and they, like, while they're in a certain lane, they can't just pass through each other. They queue. And so in contrast, the model on sidewalks is that pedestrians will move in either direction on a sidewalk, and if somebody's walking faster than somebody else, the pedestrians just kind of ghost through each other. And this is not entirely realistic, of course, but in Seattle, in practice, there are very few places that have like a large amount of people crowding on one sidewalk, and so doing some more realistic like crowd simulation is like not really worth it for the moment. Right, so we divide the world into these different agents, and kind of the first stab at solving this problem that I took was to consider discrete time steps. So effectively every 1 second, let's let's ask all of the active agents, or let's let them sense the world and say, here are the cars in front of me. Here's the speed limit of the road that I'm on. Here's how close I am to the next intersection. Things like that. And then like ask each agent, what do you want to do for this next 1 second time step? And effectively that this kind of works, but so I had a lot of problems when I did this, and some of them are a little bit. So a lot of these could be worked around, but I think the one that is like fundamentally weird is sort of performance. So you might have a lot of vehicles that are just like traveling along a long road, and they're not really doing anything interesting or making any interesting choices in the middle of the road. It's kind of only at the boundary, like the beginning and the end of the road, when something interesting is happening. And so essentially, like I tried this idea for a long time, and it kind of didn't work out. And what I wound up doing instead was called a discrete event simulation. So instead of advancing time in these like fixed time steps, every single agent kind of has the next time at which something interesting will happen to them, and you just pull the next event off of a priority queue and say, like what happens at this time, and then some interesting transition happens, and you schedule more events, and then jump forward to that time to simulate them. So intuitively, the way it works is that vehicles. Or actually, first let's think about pedestrians. So the pedestrians like can go through each other. So essentially, like they get to the one end of a sidewalk, and you can just calculate the time at which they'll get to the other side, assuming that they walk at a constant speed. And in between, then like you don't have to do any computation for them unless you're drawing. And if you're drawing, you can just do like really basic linear interpolation to say that they're crossing some distance over some time, and so you know like where to draw them at any point in time. It's like nice and parametric, easy to compute. And the thing is, like, this is also how cars work, where they enter the end of a road, and you compute optimistically what time will they get to the other end of the road and be at the intersection, and you don't really have to do any work for them until then. And of course, that doesn't explain how queuing works. So this is sort of the more detailed state machine. So cars start out kind of like parked, and let's say like 30 seconds later, they're initially like somewhere on a road. And so there's like a distance that they're crossing. This distance is usually from one end of the road to the other. And there's also like a time in which like optimistically it'll take them to cross this distance. And so the optimistic guess is like they're going the full speed limit of that road, and there's nothing in the way. So like after that minimum amount of time, they have now crossed the road. And so let's say in the optimistic case, there's nobody ahead of them in the queue. And so now they are at the intersection, and they're waiting to advance. They sort of register a request with the intersection, which is either a stop sign or a traffic signal policy. And then they go to sleep. They don't have to do anything. And then sometime later, the intersection sort of, which also has its places in the event queue, it decides to accept some turn because nobody's conflicting, or like the light changed green or something like that. And so it'll wake up that agent, and that agent moves on to the turn, and then they're back in this crossing state, and the whole thing repeats again. But of course, the interesting case is like what happens if you finish crossing a road and you're not actually the front of the queue. There's somebody else ahead of you. So then you go into this queued state, and you go to sleep, and you don't have to really like do any work. And then so up here, in the case of a car that is the head of the queue, whenever they leave one end of the road, they'll look at the person that was behind them, and they'll wake them up. So that car was queued. They'll wake them up and put them in a crossing state so that they can cross the rest of the distance. And so there's some details about how you figure out exactly where the front of a car is at any point in time. But the idea is you do the similar linear interpolation of distance over time, and that tells you like optimistically the farthest along the road that a car could be at any point in time, and then you compute the order for all of the, or you compute this value for all of the cars in order from the front to the back, and you put a bound on it. So like if the first vehicle like in the queue is moving really slowly, and like at some point in time they're only like some amount along, then the cars behind it, like even if they've spent the entire time and should be at the end into the road, they're still bounded by that vehicle in front of them. It's like plus a following distance. And so there's a bit of a detail here, which is that vehicles have both like the front and the back. And so exactly how does this work? So the distance is usually tracked by the front of the vehicle. And so here the front of the vehicle is like in the middle of this turn, but the back is still in this lane. And so the bike is the head of the queue, but really there's also this concept of like a laggy head of the queue, which is this orange car. And so the bike will not just magically jump forward and like clip into the car here, because there's this like little special case. And so how do you make this work with the discrete event system? Well, you optimistically assume that this car will kind of clear the intersection, like the back of it will clear the intersection by taking like the length of the car and like the length of the turn and the other stuff, and figuring out like if this car travels as fast as possible, what's the earliest time at which it'll be out of the way. And then at that time you compute like the exact positions of this car. And if it isn't out of the way, then right now I'm just doing like a very bad retry strategy of like checking every 0.1 seconds, and it kind of degenerates into like a discrete time system for that little section of the map. There's a little bit more complexity here, but that's like roughly how this works. So another complication. So this is a bug that happened, or that I finally found a workaround to a few days ago. So it's really simple. So this car is like a laggy head of this road because they're like halfway into making this turn. And then this long lane has somebody here. And so like what happens when this blue car starts this turn and like it needs to know where its position is along this road. So there's kind of like a recursion here because there's a cycle. Because like the exact position of this car depends on the end position of this one. But the end position of this one like is bounded by all of the cars in front of it, which ultimately depends on this one. And then the front one is dependent on this one. And so, you kind of have the cycle. And so the way that I'm working around this right now is not perfect, but it avoids some Stack Overflow. And it's to optimistically assume that the laggy head, or actually no, it's to optimistically assume that the car at the end of this queue is not a limiting factor for this one. And so you just sort of assume that there's room for this one to like clear the intersection and get out of the way. And this is going to not be true in all cases, but it's sort of good enough for now. So how do intersections work with discrete events? There's sort of some details here, but effectively, one of the main insights is that you get a lot of simplification if you only have a vehicle ask the intersection to make a turn when they're at the end of the lane and like they're in the front of the queue. Because then as soon as the intersection grants the request, you know that the vehicle has started the turn. And this kind of like simplifies a bunch of things. And that I actually forgot to mention this earlier, but in the discrete event model for cars, one thing that I'm not modeling right now is acceleration. So cars can just instantaneously stop and start. And I could go into this a little bit more detail, but essentially I think this is like modeling acceleration is not super important in the middle of the city. Kind of the points of contention that I'm interested in AB Street are things like parking spaces and like road space. Definitely like stopping and starting traffic and jam waves and stuff is an important thing, but at the moment, like that's a trade-off that I'm making. Right, but anyway, back to intersections. So intersections kind of internally keep their own state about vehicles that are waiting to enter the intersection, and then ones that are kind of approved in the middle of doing their turn. And so there's a concept of turn priorities where, like at a stop sign, some sides of the road have a stop sign, some don't. Or in a traffic light, some vehicles have a green light or a crosswalk sign, and others have like a flashing yellow, you have to yield kind of thing. And so the idea is whenever an intersection detects that like there's a free slot available, it'll consider all of the protected requests before the yield request. But if like there's not a protected vehicle that's like immediately able to go because they're at the end of the queue, like waiting, then it'll let a yield start. And there's a little bit of more like realism that could be added later. So Right. There's also a little bit of protection against blocking the box. So this is the idea of like a vehicle starts to turn and then gets stuck in the middle of the intersection and can't make progress. So by default, there's a policy where vehicles will check to make sure that there's capacity in the lane that they're trying to turn into. Where like assuming all of the cars kind of crunch up as much as possible, they'll like there's room for them. But yeah, so this policy kind of helps gridlock cases, which I'll talk about in a minute, and sometimes it doesn't. So another important thing to mention is the way that I'm modeling lane changing in AB Street is extremely weird, which is that vehicles cannot change lanes in the middle of the road, which is normally how lane changing works, but instead they can only do it in intersections. And so like here, if we have this two-way intersection, like from the right lane, you can either go straight or you can go straight and then like lane change into the left lane. And then likewise from this left lane, you can go straight or you can go straight and kind of like lane change right. And so again, there's some motivation for why it works this way, but effectively like sort of in essence, it's hard to model lane changing in this discrete event system where I kind of don't care about exactly where cars are in the middle of the road. And then also, if you have vehicles try to lane change, then that means the lane changing can fail because maybe like there's nobody lets them in. And if it fails, then you can and you will wind up in cases where vehicles are just like endlessly circling around an area, rerouting, trying to like attempt some lane changing that's like impractical. And this like really skews results if you're trying to like figure out why trips are slow. And yeah, it's sort of a mess. So at the moment, I'm not modeling it. Or rather, I'm modeling it by having it happen at intersections. So one of the biggest things that plagues me all of the time is gridlock, which is the point in the simulation in which the vehicles are stuck and can't make any progress. And they'll just like endlessly like be there in the same place. And so I've kind of like studied this problem a fair bit, and the most common root cause is like this bad modeling from OpenStreetMap, where you have like really short roads in between intersections and geometry that makes it impossible to even see what's going on. Because like effectively a vehicle can kind of wind up not fitting entirely on one of the intermediate lanes, and they like are blocking this intersection. They're blocking like two intersections at once and easily creating these like dependency cycles and stuff. But even beyond that, sometimes you have traffic signals that are too close to each other. And logically, they should be modeled as one, but right now, not doing that. And so this also causes gridlock. And yeah, so in short, this is a hard problem. There's some ideas for fixing it, and so far none of them work, but I think this is just going to take some more work. Okay, so that was sort of like the low-level mechanics of how this discrete event traffic sim work. But now let's move to a little bit of a higher level of abstraction and think about how trips work. So I mentioned like the pocket cars in city skylines. That's very explicitly like not something that I wanted to have happen in AB Street. I want AB Street to kind of have continuity of movement. So what I mean by this is that a trip starts inside of a building and it ends inside of a different building, or maybe you go on or off the boundary of the map. So like a driving trip isn't just driving. In essence, you have like the person will walk from the building to their car, which is parked somewhere nearby, hopefully nearby, and then they'll drive for a bit, and then once they're like near the destination that they want to be at, there's some kind of policy that helps them find on-street parking, and they'll drive to the parking spot, but like maybe when they get to the first one, like it's not available, and so they wind up like rerouting to the next spot. And that's what happened in this kind of example. But after they park, then they have to walk from the parking spot to the final destination. And so these are all kind of like legs of a trip. And the other ones that I haven't mentioned, you might like walk from a building to the sidewalk and then start biking. They like move from the sidewalk to the road or a bike lane and start biking. Or you might walk to a bus stop and then like wait for a bus and then ride a bus, get off somewhere, and then walk the rest of the way to your destination. So each of these is sort of a trip, and a trip is like something that begins at some point in the map, leaving say at 8 a.m. and goes somewhere else, and it like chooses a mode of transport, like the person chooses to drive or to bike or something like that. So we have a whole bunch of trips, And then kind of to logically group these together, like the trips are not each made by individual people or by separate people. Like one person over a typical day will make a bunch of trips. From work to school to, from like home to work, work to like a restaurant to home, that kind of thing. And so that's kind of how AB Street models things. Like you have people, the people take a bunch of trips through the day, and then each trip is broken down into different like pieces of the transport, which happen as a pedestrian, or in a car, or on a bike, or on a bus. And so an important thing is like, where do you get information on what a typical weekday in Seattle looks like? If you just sort of like try to uniformly at random pick sources and destinations, and say like wild guess, 5,000 people go from like neighborhood 1 to neighborhood 2, like this is not accurate. The results don't look great. Luckily, there's a government agency called Puget Sound Regional Council, and they do some very fancy modeling called Soundcast. And basically, I'm using that data in AB Street. So the way the Soundcast model works is honestly beyond me, but it looks at census data, land use of different buildings, a bunch of vehicle counts and like bike counters and things like that, and then does a bunch of really fancy stuff to figure out like how many trips there are between different regions at different times. And then they have modeling of different people that includes like age, income, and sort of a daily schedule of like they go to work at this time, they bring their kids to school at this time, and so on. And so they do a bunch of magic, and they spit out this gigantic trips file that I read in. And that's how that works. Oh, but one sort of big caveat with this approach is that the trip data right now is sort of fixed, and so you might say like I make it much easier to ride a bus in AB Street. I like really speed up this bus route. You would hope that a bunch of people would then choose to use that bus instead of to drive, for example. At the moment, I'm not modeling that. That's something I want to get to at some point, but not able to yet. So one thing that this trip data tells us is about parking. So at the start of the day, how many cars should be parked near different buildings? The way that I calculate this is pretty much the only way that I think kind of makes sense. So you look at all of the trips that begin, like the trip begins at a building and then it goes somewhere else. So then that means that you need a car somewhere near that building to support that trip if it's a driving trip. But then every time that a trip ends at some building, then like a trip originating from the same building later could reuse that car. And so there's just sort of a counter over time that like tells you how many cars are available per building, and then like the max of that, the starting case, either the starting case or the max of that tells you how many you need to seed kind of at midnight. But right now this is based on trips, and like parked cars are kind of owned or associated with buildings, and so anybody in that building can use any car associated with that building, which is like not super great, but like really people own cars. But before, about a month ago, I didn't really have a concept of a person in the simulation. I just had the trips, and so this is a piece that I need to update. But in the meantime, there's sort of a funny bug that came out of this, which is that we tried running like the weekday scenario, like 24 hours of trips, just 5 times in a row. And I kind of expected the trips to mostly be the same every day, because there's not really a lot of traffic that happens at midnight. So you shouldn't like have, like traffic jams percolate and cause the next day to be very different. But in fact, things got progressively worse and eventually deadlocked. And the reason is that we were leaking parking spots because of the way that the number of cars per building was being calculated. So that's kind of a funny bug that'll be fixed pretty soon. I'm going to take a break. Okay, so the next thing I'm going to talk about is how the simulation kind of can support some analytics that happen later in different layers of the game. So the core simulation is like mostly concerning itself with the low-level movement of different agents, and then these like transitions between different legs of the trip. And so it wouldn't really be nice to like stick in a bunch of like analytic code to do statistics on how long different phases of a trip take. Like all of that shouldn't really live in the middle of the simulation. And so the approach that I came up with is pretty simple. From like the low level mechanical portion of the simulation, different pieces will emit these events and they're all associated with the time. And so, for example, you might know that like a car entered a lane at some time, or that somebody made it through an intersection and like it took them some amount of time before they were able to start their turn. So like the low level code kind of emits these events and doesn't care what happens to it later. And what happens to it later is that this piece, which for some reason is called analytics, will listen to all of the events and then build up this state over time. And a lot of this is like extremely inefficient, and just storing like kind of like the raw events in sort of time order. And so what happens with this stuff later is that live in the UI, you can say stuff like how many. So this is traffic at an intersection or something. Like how many vehicles were like crossing this intersection per hour or per 20-minute bucket, like at different times of the day. And so like this data doesn't have to be like this line plot doesn't have to be calculated in the simulation layer. We just have to like store the raw information for it, which I guess is like intersection delays, or it's in throughput stats. And then some later code can kind of reach in, grab that event log, and process it and like produce whatever form it wants. And this has been a nice approach because the stuff in the UI is changing constantly. Like there's a lot of data visualization that's happening, and we don't really know like what we even should be doing or how we should be doing it. And so it's been nice to just like store the raw events and figure out how to process them later. And at the moment, storing all the raw events is like extremely performant. There's like no memory issues. And at the point at which this doesn't scale, there's like a bunch of easy ideas to compress the data. But anyway, something that's kind of cool that came out of this event approach is that I think it's just been like 2 or 3 weeks ago, this researcher from the University of Geneva got in touch and was interested in doing a basic pandemic model on top of an agent-based simulation. And so basically he was able to use a lot of the stuff in the event log and just directly like make one of these models. And so like I talked about the concept of people, like there's continuity of movement between people. They spend most of the time inside of a building, and then they take a trip somewhere. And the trip, for example, could involve waiting at a bus stop and riding a bus, and then they spend some more time inside of a building. But like there's just like from the different events that we have, notably this like this trip log of when different phases of the trip start. You can kind of build up a model of like how long people are spending together in shared spaces, and this is kind of the basis of a like pandemic model. So in a really short amount of time, he was able to put together this kind of model that has people start out either in this like sane, exposed, infected, or recovered state, and then based on time spent in shared spaces, probabilistically like transmit an infection. Yeah, and so this work is just starting, but I think there could be some pretty cool stuff to learn from it. And yeah, just it's something that's a little bit relevant for the times. The other way that like unexpectedly the traffic simulations architecture like lended itself to tacking this extra model on is that like once say transmission occurs, you might want to wait some variable amount of time before transitioning somebody from like an infected state to a recovered state. The discrete event simulation exactly kind of lets you do this thing where it's like a transmission event occurs at some time, and then you can schedule in the future an event to like do another state transition. And so, yeah, like I didn't really design anything expecting this sort of thing to be tacked on to the simulation. But like happily, the architecture has kind of worked itself out to where it's been easy to do. Cool. Here's another intermission. I'm gonna pause for a moment. All right, so moving along, now that we've talked about how the map is built and how the traffic simulation works, I'm going to talk about the kind of topmost layer of the code, which is called the game crate. And it sort of controls all of the interactive logic for all of the interesting stuff. So back in 2018, when I started this project, kind of like looked around for existing libraries and game engines and stuff, and at the time, a bunch of them were just bindings to native libraries that kind of had awkward APIs in Rust, or they had like, like if you had a button click, there'd be like a callback and very awkward borrow checker issues. So in my infinite wisdom back in 2018, I was like, let me just roll my own. So yeah, let's talk about how that went. So game loop 101. There's some input. The mouse is moved or somebody presses a key. And you want to handle it, and then every so often you draw your state. So, easy. And so in retrospect, this amount of the game crate has like gone through all sorts of churn, and in short, if you have like a clear vision in mind, when you start, it's a lot easier to build things. But I don't even know really what all AB Street should do, and so. This is an image of what the sandbox mode used to look like. There's kind of like a bunch of different pieces of functionality just like stuck into one gigantic menu. And so like besides like looking bad, the sort of problem with this UI is that it didn't really organize all the different pieces of functionality together. I think like the very version 1 of this code was like there were these independent pieces of like features that would let you like examine someone's route or examine the turns of that originate from an intersection or something like that. And just like there were 40 of these, and they were like structured as plugins, and the plugins would either demand exclusive access to everything or would kind of be non-blocking. Anyway, like I've been through many iterations of the architecture, and like they're all a mess. Things got really good, or things got much better back in November when Ewan joined, and we like actually had proper UX, and I knew what to build. So TLDR, like design is important. But yeah, so let's talk about how things work today. So effectively, the game is broken down into different states, and so you have a state for like the main menu where you select stuff. You have a state for like running the simulation live and kind of interacting with everything there. And then maybe you enter edit mode to make some changes, and that's a separate state. And then inside of edit mode, you enter like the stop sign editor, and that's another state. And so these things form a stack where like once you leave the stop sign editor, you pop back to the edit mode and so on. And so the kind of the key or the main structure of all the events or of all the states is that whenever they handle an event, they produce a transition, and the transition says to do something to the stack, which is usually stay in the same state or pop back to the previous one or like push on a new state. Then at the same time, there's this there's sort of like all the persistent stuff that isn't like per that one state. Things like the map, which is mostly immutable, the simulation, which is highly immutable, layers of pre-drawn stuff, the color scheme, a bunch of stuff like that. And so in the event, you kind of have the event context, which tells you, which is like the hook into the GUI library. It tells you what event happened. And then you have like all of this app stuff that you can do. So there are some kind of problems with this approach. For example, in the sandbox mode, whenever you enter edit mode, it's you have to like take a copy of the simulation in its current state and sort of like take one clone there. And that clone is sort of unavoidable, but then whenever you enter the traffic signal editor, because of the way it works, I'm also cloning to pass in there. And it's like, logically, there's sort of only one of these suspended sims that exist at a time, and it would be nice to kind of pass it back and forth, but because there's a stack of states, and because I want to avoid like lifetimes and borrow checking like in what the states store, there's some places where like I clone, and I'm not super happy about it, but at the moment it's okay. The other pattern that's kind of weird here is like, let's say that, so like this example, let's say that you've opened up a table that has a bunch of different trips, and you're like viewing stats on the trips, and you click a trip, and you want to close the table, so to pop, and then to like modify the state of sandbox mode by opening up a new panel, which is just like a little piece of, which is like the panel logic as some state inside of sandbox mode. So this is kind of awkward. Like logically, what's happening here is that like sandbox mode is calling a function, and the function is to like run the trip table state, and like you want to handle the return value by like opening a panel up in the sandbox mode, but I can't really express that today, and so instead there's a transition called pop with the data that will do a pop, but then pass you like the top of the stack. And so in this case, it'll like take the sandbox mode, like downcast that state back into like the sandbox mode state, and then like do the mutation there. Anyway, it's kind of funky. There's probably like a better way of doing this, but overall it sort of works. And let's actually like just make this more concrete and look at an example here. So I really hope I'm still recording here. This is a state for one of the challenge modes to like optimize a single person's commute. This state has sort of its own like inner fields that kind of only it has access to. It tracks the person that we're optimizing. It sort of tracks the last time at which we've checked the score and updated some stuff. This top center panel is this guy, and then yeah. So the interesting bits, we have like the event handler, and kind of it does this like initialization where the very first time it runs, it launches an info panel, and then it'll see, okay, has any time passed in the simulation? If so, redraw that top center panel, and then remember the time. And the reason we want to redraw is that this thing says how many trips are done, and it sort of like sums up the trip time. So anytime time passes, this might have changed, and so it wants to recalculate it. And of course, doing this constantly is not efficient. Like, it could be smarter about waiting for trips to be done, but whatever. This is simpler. Then the next piece is so this top center panel has a few buttons, notably edit map, this little like info panel, and then this little thing here is like a target, or it like locates the person that we're optimizing. So we like take the event and kind of feed it into this panel. And as an outcome, something might have been clicked, and so actually, hang on, my night mode thing is on. There, you can probably see the screen a little bit better now. And my eyeballs are now very sad, and I will not sleep tonight. Darn. Right. So if you like click the edit map button, then we push. We do this transition push, and then like enter in edit mode. Likewise, if they press instructions, we jump to this like cutscene thing. And if they decide to like locate the person, we open up an info panel. And then this is some stuff that'll look through and see if the simulation is done and kind of deliver the final score and do some stuff there. And the draw is very simple. Most of it's this like, it'll draw the map by default, and then it draws this panel, and that's it. And I guess we can also look at how this panel is constructed. Yeah, why not? So, ooh, that's bright. Yeah, so like this thing consists kind of two rows with like the text, the info button, separator, a button, and then a bunch of other stuff. And so that's like roughly reflected here, where we have like a column. First part of the column is this like little header that says like optimize the commute. I think this just draws it with oh yeah, this is like a special thing that'll like draw it with the text and the info panel and the edit map like this, just to help our function to do that. And then the second row, we have the button to like locate the person. We have some layouting hints like add a margin, and then we draw some text and add a margin, then draw some more text, which is like the total trips, yeah, and so on. So yeah, that's just sort of an end-to-end example of one of the states to make some of the stuff more concrete. Yeah, so the game crate really has changed a lot over time. There have been some like high-level patterns that have emerged, and I think like I'll at some point refactor them and make them a little bit easier to share with other code. One of the main things is info panel. So you can click on different objects, and this will open up a little pop-up that doesn't like cover the rest of the simulation. It's just like floating. And this thing has different tabs you can click on, and it sort of constantly updates. So one of the big principles about the way that I've written a lot of the game crate is that just like anytime anything potentially changes, recompute from scratch. Don't be clever and like incrementally update stuff unless like it's absolutely necessary from a performance standpoint. And it's just so like this kind of winds up being simpler, at least the way that I've structured it. And so far there have been very few places that actually are slow to update constantly. So whatever. Yeah, I guess some other stuff that's kind of like wound up happening is the game treats the being zoomed in or zoomed out as fairly different. A lot of controls kind of change and like what's allowed changes, uh, and that's most of this is sort of like UX stuff. But yeah, like maybe there's some more code structure that could like distinguish these two views a little bit more. Um, and like another sort of funny thing, you'll notice in the example that I showed. This actually isn't a state. This like event handler like takes this extra sandbox controls things, and it's not just returning a transition. It's like returning a few other things, and that's because at the moment something called sandbox mode, which is a complete misnomer. It's the state of the game, or it's the state in which like the traffic or like the simulation is running, and you can kind of interact with the map. And like on top of this, there's a whole bunch of different gameplay modes that specialize different stuff. Like in the optimized commute thing, it'll draw that particular panel and it has a certain definition of score and so on. And yeah, so like this is like in some languages you might kind of use inheritance and say like there's a generic simulation state or a simulation mode and you want to like inherit from it and specialize some stuff. There's kind of like two different ways I see of doing it in this case. At the moment, I have like this master sandbox mode state, and it does all the common stuff, and then it sort of contains an inner one of these like gameplay modes and just like calls into it. The alternative here is to like invert the pattern and make optimized commute and anything else be its own normal state, and then kind of like contain some of the sandbox mode stuff as members and like call into it instead. And I don't entirely remember why I did it this way. I think I've gone back and forth between the two, and at the moment I'm on this one. And yeah, I don't really want to talk about that. Quick break. All right, so yeah, getting a little bit away from implementation details. I mentioned that this thing is like in a constant identity crisis between being an urban planning tool and being a game, and that's because I'm not really a game designer, and I kind of don't want to be a game designer. But at the same time, like I've sort of signed up to make this thing that like acts like a game, and so like one of the ideas I've had for like a challenge mode in this game that's not just like this undirected sandbox thing is challenging people to like fix traffic signals. And so the story here is that I don't have any data about how traffic signals are timed, and so I'm like making complete heuristic guesses about how many phases there are, what movements you can do during the different phases, how long the phases last, and stuff like that. And these heuristics are absolutely terrible. And so as a result, there's a bunch of like unrealistic traffic jams that form because of the dumb traffic signals. And so like I have a bunch of ideas for kind of like fixing this from a software engineering perspective, but then, from a game designer perspective, it's like, wait a minute, like why not just make the player do it and say like, oh, how well can you like optimize the existing traffic signals that got broken for some reason, and then the player does the work for me. It'll be great, right? So this is story time. So I was doing some play testing of one of the challenge modes, and because it's my my favorite thing in the world, I decided to turn some parking into some bike lanes. And then I was going through and seeing what trips were impacted and looking for any slow ones. And very unexpectedly, somebody walking on the other side of the map got like 5 minutes slower, and I was kind of confused. So if this was like the live talk, I would like pause and ask people to give me their wild theories. So basically what happened is at the very beginning of the simulation, to set up a random number generator determines stuff like pedestrian speeds and like exactly where cars are parked and stuff like that. It's like earlier I talked about how like we kind of compute how many cars are needed at midnight per building, and then like there's an algorithm that kind of like finds all of the available parking spots near a building and like tries to fill in cars close to the building, and there's like a little bit of randomization there. So anyway, this bug was whenever you edit the map, in this case I took away some parking spots and made bike lanes, and so the random number generator like had a different amount of parking spots to like shuffle, and we ended up calling the random number generator like a different number of times. And so when it was time to like generate the pedestrian speed, it actually like kind of got out of sync with the original scenario and like made them way slower or something. And so the solution here is easy. You kind of fork the random number generator by like creating a derivative RNG. And so like before you do all of the parking randomization, you generate a single number and then you use that as a seed to a second number generator, and then that one goes and like does all the parking stuff. And so then that way you isolate the effects. It doesn't affect the pedestrian speeds. Anyway, that's just kind of a funny bug, and the sort of stuff that you deal with a lot working on this. So moving right along. Okay, now we're going to talk about so going from like high level back down to a little bit low level. Yeah, so I mentioned 2 years ago that the different options for like how do you draw stuff and handle events and like do like widgets, GUI widgets and all that. The like options were a little bit nebulous, and so for better or worse, I wound up with my own. It's called Easy GUI, which is a terrible name, and I need to come up with something better. And I'm talking about this in particular because, or I'm talking about Easy GUI in this talk, because I think I'm like reasonably close to cleaning up the API, and I want to put it on crates.io soon, so that other people can kind of like enjoy this monstrosity that I've concocted. But anyway, so what is this thing? So it uses OpenGL, and it runs natively on Windows, Linux, and Mac using there's some OpenGL. A very nice OpenGL wrapper called Glium, and then to get the OpenGL context set up, it uses a crate called Gluten, and then there's a crate called Winit that does like window management and events and input and stuff like that. Then on the web side, it uses a crate called Glow, which is GL on whatever, and then Winit, and then standard web. And kind of notably, like a bunch of widget libraries that do web have like completely different controls in web because like they're using the browser's native ability to do stuff. But I'm not doing this. I'm like literally drawing all of the same stuff that I do natively in OpenGL, which has its trade-offs, but I think it's kind of an interesting approach. And so this crate does a bunch of stuff. In particular, it gives you a bunch of nice 2D drawing primitives and ways to like upload your geometry once and efficiently redraw it later. Gives you a canvas that scrolls. There's like a single shader baked in, and it's super simple. And then kind of notably, the library only supports vectors. There's no like 2D texturing or anything like that. And so like all of the images in the game are SVG files. This awesome crate called micro SVG transforms the SVGs and like deals with a bunch of the complexities there. And then there's a crate called Lion that tessellates polygons and just sort of gives you geometry out of that. So then I like upload the geometry to the GPU and boom, done. And what's maybe like a little bit unusual about this is that this is also how text rendering works. So the text is fully vectorized. Micro SVG has a dependency on a library called harfbuzz to do text shaping. And so at the moment, this is preventing the web demo from working. But in a few months, the guy working on micro SVG he's working on a port of harfbuzz called rustybuzz, and it's going to be like native Rust. And so then it'll be possible to do vector text in native Rust, which means like super easy WASM version, which is like awesome. But anyway, yeah. So the Easy GUI does like all this 2D drawing stuff, and then on top of it, it kind of like attempts to be this GUI library, and so it gives you widgets to draw stuff, buttons that change state when you hover, sliders, drop-down menus, autocomplete, a bunch of the standard stuff. It's pretty much like entirely dictated by what things UN designs and decides should be on AB Street. And then this is not a piece that I like very much, but to like organize the different widgets, there's some layouting using like Flexbox, which is the same thing that's in like browsers for CSS, and there's a crate called Stretch that does it. I'm not super fan of Flexbox layouting because a bunch of stuff that feels like it should be intuitive isn't. And there are a bunch of caveats. Maybe it's just with the implementation of how I'm gluing like Stretch to my code, but like, for example, if you ask for margin or padding on objects that are not rows or containers, like it just silently doesn't work. And I don't particularly know why. But anyway, I think I figured out a lot of the tricks in Flexbox at this point, and I'm like wrapping them up in nicer APIs. And so it's pretty good. And then, yeah, the other thing this library does, which maybe should be a library on top of it, I don't know, is a bunch of like data viz stat stuff. So at the moment, there's like line plots, scatter plots, and tables where you can kind of like sort by the different columns and filter stuff. And I'd like to stop being in the business of like coming up with like plotting software. Like there's a library called Plotters that I'm excited to try out, but at the moment it's been nice to like, or I mean like the reason I've built everything kind of from scratch is that I have like full control over it, and that lets me do stuff like have interactive graphs. Oh, I maybe don't have an example of one. There's an example earlier, yeah, where like you can take your mouse and like hover over any of the lines here, and there's like a tooltip that'll pop up and like describe the value at exactly that point. And so like doing that with a static plotting library like Plotters probably wouldn't be as easy. Yeah, but anyway, oh, I promised the demo here. So yeah, so I said this thing runs in the web. Yeah, let's try it. So there's going to be this like awkward few seconds in which you wonder if I'm crazy, and I wonder if I'm crazy, and then yeah, cool. So I mentioned that the text rendering isn't there yet, so that's why some stuff is going to be a little bit weird. But you know, proof of concept, exactly the same thing you saw in native, modulo the text and some coloring issues, is running in a browser, which is like kind of amazing. And it's a little bit laggy, but you know, there's some work to do. But the proof of concept is here. It'd be super cool to like run this thing in the browser, not have to have people download it. Yeah, but yeah. So how did I start to get this running on the web? I didn't plan for this at the start. I think like a few months ago, I was just like, it's time to do it. One of the big blockers that I had been tracking was the Winit crate that does like event handling. The support for the web stuff landed in like January, and I was like, okay, there's no excuse I have to try this out. And honestly, like the whole process was super easy. I think it only took a couple days to get things running. I sort of like had to reorganize some of the backend stuff and figure out how to glue things together. But effectively, what I did was like I just took the code that I had and like ran cargo web start, and like a bunch of stuff initially broke because it's like I depend on a crate that isn't WASM friendly. But there were a few of those that I was easily able to replace or to work around. And then yeah, so the reason the port was so easy is that I organized the code that talks to the OpenGL libraries, either Glium or Glow or the Glow on WASM, in a very like particular way with a very small interface where it's like just effectively like go upload this list of triangles with like certain attributes on them, and like please draw this thing. And so like the code for each of the backend implementations is like literally about 300 lines. This is like pretty cool that it's this simple. So like I know some people are interested in like Vulkan and what is it like? Yeah, all the new like stuff that's fancier than OpenGL. I don't really have knowledge of that, or I'm not like super interested in it. But if somebody like wants another backend, like theoretically it's 300 lines. You just have to like upload your triangles. The other little Rust trick that I want to talk about is like a lot of times I've seen libraries that support multiple backends like kind of have a trait describing the interface that the backend has to implement. I didn't really see the point in doing that for this sort of thing, because it's like when you pick a backend, you're going to pick exactly one at compile time, because like you can't compile Glium in the like the WASM 32 target at all. So like in the EasyGUI library, there's this like backend module, and like based on the feature that you like choose in the cargo file, it'll just like pull in a different backend, and then the rest of the code can just like reference the backend, and it doesn't care which one it is. And so this is your like compile time like trait workaround thing. And yeah, it's super easy. So more about the experience with WASM. I'd love to figure out how to like just generically redirect all of standard out and standard error to like the console. I have not found a way of doing that. You can at least say whenever something panics, like print something to the log. But I haven't figured out how to get stack traces here. So like the text is sort of small, but like here you can see like I got my panic message, and then like the stack trace is nothing to do with my code. Like actually no, wait. Sandbox mode event. Yeah. Anyway, like I guess there are no line numbers, and yeah, this part needs a little bit of work, I think. But yeah, overall the experience is not bad. So this is funny. So AB Street like reads a bunch of random files, like the SVG files and all the like map data files and stuff like that. So at first, I think like most of the time converting to WASM, like I sunk into trying to replace the file system by like having the like reading from a server, just like download the same files from the server that you would normally read from the file system. And like for the life of me, I couldn't get this to work. All the stuff to like make what is like the XML HTTP request things. Like I tried a whole bunch of stuff between like standard web and the other thing and couldn't get it to work. At the end of the day, the thing that worked that's like super easy is that like Rust has this built-in macro called include bytes where it just like at compile time like reads in a file and like smushes it into like a const array into like the static section of your like binary. And so I was like, okay, cool. Like does like are there limits to this and can you do it on a whole directory? The answer is there's a crate called include_dir that does exactly this. And like I'm fitting 500 megabytes into like one WASM binary, and like this is completely 100% fine, apparently, because it works. And I'm sure like longer term there's something better to do, but at the moment like cool. Okay, so the second round of can you solve this bug? This doesn't happen on native, but in WASM, when I was like loading certain maps, I get this like deserialization error from Serde, which is this big ass integer like is like what was found, but it was expecting a usize, and so the culprit here is kind of funny. It's this is like I think 2 to the 64 minus 1. And it turns out that WASM is not WASM 64, it's WASM 32, and so usize is just 32 bits. And I had a dependency that was storing like usize max and serializing it, and so that doesn't work if you're reading it in 32 bits, and so there had to be a little bit of a workaround there to rewrite it into like a 32-bit usize. But anyway, that was kind of a funny thing. So one reason I haven't like released the Easy GUI crate to the wild yet is that there's some big problems with it. I guess kind of the main one that I want to focus on here is this like way of figuring out, of what button click happened. I have this like this outcome enum, which is literally it just tells you sort of a string of like what was clicked, either like X or these different buttons, and like using strings is like not super type safe, although in practice I think I've like never had a typo, or it's like extremely obvious to find the bug when there is a typo. But anyway, like this is not super nice. I'd like to have a way of plumbing in like a user-defined enum for the button click, but just have to like kind of work through that. So all right, last part of the talk. I promise we're almost done. So so this is a big project. I've been working on it for 2 years, and I think there's like super exciting stuff left to do, and many cool directions this could go. But I'm like one programmer, and I could really use more people. So just I'm gonna quickly describe some of the stuff that I think could be nice to have collaborators do. On like the sort of like map data layer, if you're into GIS or anything like this, you saw the like terrible map geometry problems that I saw. Like maybe you have better ideas how to fix this, or I don't know, maybe like you're super into machine learning and you have access to like satellite or LiDAR data, and you can like just figure out how to like vectorize Seattle and get all the curbs and stuff. Like awesome. Like if you can go do that and I can read in this data, like that would really make AB Street cooler. Or like a simple starter project might be, for example, the heuristics that assign phases to traffic lights are like really dumb, and you can probably make them better with like not a lot of effort. And I think that's like a well-contained starter bug. Also, so AB Street is sort of specialized to Seattle, but it's principally built on OpenStreetMap, and I have some support for importing other maps, but there's like a little bit of stuff left to do, and other cities, like per city, there's sort of some work that requires finding data sources in like trip demand data, the equivalent of like the Soundcast data, stuff like that. So if you're interested in seeing this run anywhere else, I'd love to help. And like basically you drive the work, but I help. That's the way this could work. There's a whole bunch of stuff in the simulation layer that needs improvement. For example, simple stuff like we need an elevation model so that bikes don't go the same speed up hills and down hills. The modeling of buses and transits, I didn't focus on it because it is very primitive. There's no light rail today. I think stuff like ride sharing would be super cool to add in. And then also maybe you're not a programmer, but you are interested in kind of game design. Like I'm mostly a programmer, and so I don't know how to like take this fun thing that or this complex thing that I've built and make it fun. But maybe you have ideas about how to structure the challenge modes or how to like create tutorials or like leveling and progressions and stuff like that. Game elements. If you're interested in that, then yeah, please get in touch. Yeah, so I'm gonna describe a few of the like specific projects that like I could use help with, and this is definitely not a complete list or prescriptive or anything, or just some examples. So for example, let's say we wanted to start modeling Seattle's light rail. I think it'd be like actually pretty straightforward. So the map model kind of layer needs to be updated. The like physically where the track goes is already in OpenStreetMap, and I think we could just like model this as a new lane type. By the way, like sidewalks and driving lanes and parking lanes, like all of these are just kind of generic lanes with the different types. And yeah, so then like figuring out which buildings are stations to enter the thing, and then kind of like updating the map model in a small way to mark that. It's a little bit unclear how to handle like the boundary of the map with light rail. But yeah, anyway, so the simulation layer for like making the trains move along the track. I think since like trains do get blocked by trains in front of them, like using the existing like lane modeling and all the existing queuing would kind of work. There's a little bit of work to like model people entering and exit stations. And then possibly like the hardest part of this is probably the UI. Like how do you draw light rail track from a Z ordering perspective? Like if the track is underneath buildings, or it's like at street grade, or it's like a bridge. I think like that's a little bit unclear how to do. And like there's some bridges and tunnels today in the game, but like they don't work so great. And yeah, so another example project that could be fun. Like let's say you want to design a whole new bus route that doesn't exist today because you have an idea for it. I think like this would be like a fun UI kind of project to like figure out how to place new bus stops and let players draw routes. And then it would be a lot of taking like the existing transit modeling and kind of improving it. So adding in stuff that has schedules and number of buses. So like right now every route has exactly one bus that serves it, which is not so great. Yeah, and so I've seen a lot of talk especially on Twitter lately, about allocating more space to be like pedestrian only, or to like reduce the speed of cars in it so that people can like more safely walk on the street and practice social distancing and stuff like that. And this is exactly the sort of thing that I like started AB Street to solve. People like have this idea about changing the world, and they want to like communicate about it more clearly, or inspire other people to be excited about it, like that kind of thing. So I think this sort of thing could be potentially done pretty quickly in AB Street. There's already a way to model lanes and intersections under construction. I think there could be a modification to just like change it to be access restrictions so that only pedestrians and bikes could go in. And then potentially this could be an excuse to model like pedestrian plazas instead of just like linear movement of pedestrians along sidewalks. But yeah, so if people are inspired by this sort of thing, get in touch. Oh yeah, and so just this morning I was talking to Ewan about different ideas for visualizing statistics on trips. So for example, you might wonder like where are different trips throughout the day starting and ending. And you might imagine like breaking down this kind of data by individual buildings, which is probably overwhelming, or maybe like by city blocks or even entire neighborhoods. You might wonder like when do different trips start, how many are biking versus driving, and then once you sort of like measure some information about all of these trips, like which ones of them are slow, which ones of them are slower or faster after the player makes some changes, and stuff like that. And so like there's a whole bunch of ways to explore this data, and we have a billion ideas. But it takes time to implement them and prototype them and stuff. But if you're into data viz, this is like super fun. Oh yeah, and then I have a hard CS problem that maybe somebody has an idea about. Today, the divisions of the map in AB Street are just it's clipped to different bounding polygons that I made up kind of arbitrarily. We'd like to come up with better ones, and so given all of the trips from the original Soundcast data, how could we like split up Seattle into different possibly disjoint regions that like minimize the number of trips that cross the boundary, so that we have a lot of trips like entirely in the map. This is probably some cool like graph problem. Oh yeah, and so I just have so this is basically the end of the talk, but I have a few random things that I didn't know how to fit in elsewhere. One is just sort of like a retrospective on using Rust. I think I originally tried it back in like October of 2014. I just like gave it a shot for a few days, got kind of confused and gave up. This was like pre 1.0. And then let me think. Back in January of 2018, I gave it a shot again. This was after 1.0, and it was like suddenly so much better. The compiler error messages were magical. The one I think I appreciated in particular was like if you're trying to use a method that is implemented for some struct, but only if you import a trait. Like the compiler just tells you to add in a use for it. And I actually remember back in 2014, I think I was confused by this concept of importing the trait. But then like the compiler just got like so much better. Non-lexical lifetime has landed like probably a year ago at this point, and that made a bunch of code easier to write. I don't even remember what it was like to write before that. And then something that landed just a few releases ago that's super cool is profile overrides. And so most of the time I'm just changing the game crate, but it depends on a bunch of stuff that like it'd be super nice if you could compile things like the OpenGL drawing libraries in release mode so that it's very fast at runtime. But you don't want to like compile everything in release mode all the time, because that's a very slow like prototyping cycle. So profile overloads are magical. They give you the best of every world. This lets you say like any of your like third-party dependencies that like aren't in your local code base, compile them in release mode once, but then everything local, compile it in debug mode. So this is like exactly what you want. And then also, if you're on Linux, there's an alternative linker called LLD, and if you configure it, the time to like link large projects just drastically goes down. And so this is super cool. And then yeah, so the very last slide, just notes about the performance of AB Street. Overall, like I'm going to go ahead and say it's unoptimized. I haven't really focused on the scale of everything yet. But I will say that like kind of by default, the performance that comes from using Rust is awesome. And from my understanding, like the reason things are so good is that there's not garbage collection, unless you opt into it, of course. And like more importantly, there's no chasing pointers through memory. So like, if I have a vector of some complicated, deeply nested structs, like there's no like all of that's smushed together in the heap. So like cache locality happens and it's awesome. And oh yeah, so the other super cool crate that I'll mention, if you do any pathfinding, like I'm sure you know about like Dijkstra's and A-star and stuff like that. If you have really big graphs and you're doing like many thousands of queries against the graph and the graph doesn't change too much, there's a very fancy algorithm called contraction hierarchies that'll like pre-compute just once these like shortcuts through the graph, and then like when you're querying to get shortest paths, you can do it like way faster. And that crate has like saved my life. Yeah, and so that's the end of the talk. Thanks for watching.